Hello students, ഇന്ന് നമ്മൾ continuously differentiable functions എന്നുള്ള concept പഠിക്കാൻ പോവാണ്. പിന്നെ അതിന്റെ ഒരു characterization. So first we will start with the definition of continuously differentiable functions. So suppose that f is a mapping of E to Rm, where E is an open subset of Rn, and we say f is continuously differentiable in E if f dash, the derivative of f, is a continuous mapping of E into L of Rn, Rm. നമുക്കറിയാം f dash of x എന്ന് പറഞ്ഞാൽ it's a linear transformation from Rn to Rm. So where does x come from? X comes from E. So f dash, when viewed as a function from E to L of Rn, Rm, it should be continuous. Derivative is continuous. Then we say f is continuously differentiable. So continuously differentiable function means derivative is continuous. അപ്പോൾ നമുക്ക് ഇതിനെ കുറച്ചും കൂടി പ്രിസൈസ് ആയിട്ട് ഡിഫൈൻ ചെയ്യാം. ദാറ്റ് ഈസ് ഫോർ എവറി എക്സ് ഇൻ ഇ I want a continuity of f dash x. f dash x is in L of Rn, Rm. So നമ്മൾ എങ്ങനെ continuity പറയാം? Whenever the points are closer, corresponding images also must be closer. അങ്ങനെയാണ് നമ്മൾ continuity പറയാം. So നമ്മൾ എപ്സിലോൺ ഡെൽറ്റ ഡെഫിനിഷൻ ആണ് യൂസ് ചെയ്യുക ഈ ക്ലോസ്ഡ്നെസ് പറയാൻ. So images must be as close as you want. So norm of f dash of y minus f dash of x, they are the images under f dash. That should be less than epsilon whenever the points x and y are close in E. So norm of f dash of y minus f dash of x is less than epsilon for all y in E with norm of y minus x less than delta. If this happens for every x in E, then we say f is continuously differentiable. Okay. So what is meant by this norm of f dash of y minus f dash of x? Remember, both f dash of y and f dash of x, they are linear transformations from Rn to Rm. So they belong to L of Rn, Rm. So this norm here, that is the norm of L of Rn, Rm, or in other words the operator norm of the linear transformation f dash. Their difference must be less than epsilon whenever norm of y minus x is less than delta. So what is meant by this norm? X and y are coming from E. E is in Rn. So this norm is the norm in Rn. So these things are understood. Okay. Shall we move to the next slide? Next is a characterization of continuously differentiable functions. One more thing I forgot to mention here. The notation is f belongs to C dash E whenever f is continuously differentiable. So C for continuity and dash for differentiability. So we say, or we write, f belongs to C dash E whenever f is continuously differentiable. So next is the characterization. F is continuously differentiable in E if and only if all the partial derivatives djfi exist and are continuous on E for all I from 1 to m and for all j from 1 to n. So what is meant by djfi? Remember, djfi is, what is djfi? Dou fi by dou xj. ഇതാണ് djfi. So what is meant by fi? Here given is f. So what is meant by fi? F is a function from E to Rm, where E is a subset of Rn. So f has m coordinates. Those m coordinates are f1, etc., fm. Understand? And if x is a point in E, I can write x as x1, etc., xn. So this f as an m tuple, this is the notation, but as a linear combination of the standard base elements ui, this is the notation. Sigma I equal to 1 to m si vector ui, where ui is standard basis for Rm. And whenever x is in E, namely x equal to the n tuple x1, etc., xn, this is the linear combination notation for x, where ei is the standard basis for Rn. So f is continuously differentiable if and only if all the partial derivatives of all the fi's with respect to all the xj's are continuous. That is what the theorem says, and we will prove the theorem. First of all, we will observe a few things. If x is equal to the ordered n tuple x1, etc., xn, as in the previous slide, then what are those xj's? They are precisely x inner product ej, right? You write x as x1 e1 plus etc. plus xn en, as in the previous slide. Then look at x inner product ej. So it is x1 into e1 inner product ej plus etc. plus xj into ej inner product ej plus etc. plus xn into en inner product ej. But ei inner product ej equal to 0 whenever I not equal to j. Therefore, what you are left with is simply xj into ej inner product ej. But ej inner product ej is equal to 1. So xj is x inner product ej. Similarly, fy, the ith coordinate of f, is f inner product ui, where ui serves the standard basis for Rm. So these things we have to observe and understand. Now we will start proof of theorem. So first assume that f is in C dash E. What I have to show? I have to show all the partial derivatives djfi exist and continuous. But existence we have already proved in a previous class, maybe in a couple of classes earlier to this. So now we have to prove only continuity. we have to show all the DJFIs are continuous. Existence we have already proved. Remember the previous slide, this also we have proved. What is matrix of f dash x? Matrix of f dash x can be represented in terms of the partial derivatives of f. So this m by n matrix, d1 f1 at x, etc., dn f1 at x, etc., d1 f1 at x, etc., dn fm at x. This m by n matrix represents the matrix of the linear transformation f dash x. Okay, given a matrix like this, what is its jth column? It is precisely that linear transformation applied to Ej. So f dash x Ej equal to the jth column of f dash x. But what is jth column of f dash x? It is the vector in Rm given by dj f1 of x, dj f2 of x, etc., dj fm of x. That m tuple, or in other words, in the linear combination notation, this is the mth column. I will show you the matrix again. So what is the first column? What is the first column? d1 f1, etc., d1 fm, that m tuple. So in linear combination notation, it is d1 f1 of x times u1 plus etc. plus d1 fm of x times um. That is the first column. What is the jth column? That is precisely this. dj f1 of x times u1 plus etc. plus dj fm of x um. Okay. Now I want to obtain the ith coordinate of f dash f x into Ej. So what is the ith coordinate? How to get it? Take inner product with ui. If you are given a vector and if you want to get its ith coordinate, what you have to do? Take inner product with ui. That's what we have observed. So the ith coordinate of that jth column, namely dj fi of x, is obtained by taking the inner product with the ui of this vector f dash of x into Ej for all I and j and for all x in E. Sorry. Hence, dj fi of y minus dj fi of x. So when you compute dj fi of y, I will get here f dash of y into Ej inner product with ui. So when you compute this difference by property of inner product is distributive over sum or difference. So you will get f dash of y into Ej minus f dash of x into Ej inner product with ui. But f dash of y into Ej minus f dash of x into Ej is precisely f dash of y minus f dash of x into Ej. Right? Because for linear transformations, let us say capital A and capital B, ax minus bx is precisely a minus b times x. where X is a vector. So use that property as well as the property that dot product or inner product is distributive over a sum will enable you to write the left side as this expression. Hope you understood. Let us move to the next slide. What I have to show? I have to show all the DJFIs are continuous. Remember, DJFIs are real functions. So how do you measure the distance in real numbers? By using modulus. So modulus of DJFI of y minus DJFI of x equal to modulus of the right side in the previous slide. So modulus of f dash of y minus f dash of x into ej inner product with uy. Dot means dot product or inner product. Now use what is called Cauchy's-Squartz inequality. So what is Cauchy-Squartz inequality? Modulus of x inner product y is less than or equal to norm of x into norm of y. So use that. So you will get this expression less than or equal to norm of f dash of y minus f dash of x into ej into norm of uy, where it is understood that these two norms are norms in Rm, the codomain. Okay. Now again, this is less than or equal to, use the inequality norm of a of x less than or equal to norm a into norm x for a linear transformation A. So here I have the linear transformation f dash of y minus f dash of x applied to the vector ej. That is less than or equal to norm of the linear transformation, operator norm. Norm of f dash of y minus norm of f dash of x into norm of the vector, norm of ej, where it is understood that this norm is norm in Rn, the domain, into norm of uy. But remember, ej and ui, they are the standard basis for Rn and Rm respectively, so that norm of ej is 1, norm of ui is 1. So finally, this is equal to norm of f dash of y minus f dash of x. Understand? Now, what was our assumption? F is continuously differentiable. That means f dash is continuous. That means this right side can be made as small as you want whenever y is close to x. But the left side, this quantity is less than or equal to this right side. So left side also can be made as small as you want whenever y is close to x. This is precisely saying DJFIs are continuous for all I and j. മനസ്സിലായെന്ന് വിചാരിക്കുന്നു. So this is one part. Let us go to the reverse part. So converse. It is enough to take the case m is equal to 1. That means f is from E to R. It's enough to take that case. Why is that? I want you to justify why it is enough to take the case m is equal to 1. That means now f is a real function defined on E. F is from E to R, where E is an open subset of Rn. I will give you a hint. A vector function is continuous if and only if its components are continuous. And a vector function is differentiable if and only if its components are differentiable. So that is the hint. And with that hint, I want you to justify it's enough to take the case m equal to 1. That means f is a real function. Okay. Now what is our assumption for the converse part? Our assumption is all the partial derivatives are continuous. And what I have to show? F is continuously differentiable. Okay. So to prove f is continuously differentiable, first you start with an x in E and epsilon greater than 0. And you want to show norm of f dash of y minus f dash of x is less than epsilon. Okay. Now E is open and x in E. So there is an open ball S centered at x sitting inside E. Okay. Now for the converse part, what we are assuming, all the partial derivatives are continuous. What are all the partial derivatives? Remember here f is a real function. So f has got only one component. So I will denote it by f itself. So the partial derivatives are d1f, d2f, etc. dnf. These are the n partial derivatives of f. And all these are assumed to be continuous. So since d1f is continuous, for this epsilon greater than 0, I will get a delta 1 greater than 0 such that dj f at y minus dj f at x is less than epsilon by n. And since d2f is continuous, modulus of d2f y minus d2f at x is less than epsilon by n whenever norm of y minus x is less than delta 2 and so on. And you will get a delta n greater than 0 such that norm of dnf at y minus dnf at x is less than epsilon by n whenever norm of y minus x is less than delta n. Okay. So corresponding to this epsilon and corresponding to the functions d1f, d2f, etc., dnf, I got delta 1, delta 2, etc., delta n, positive numbers. Okay. Now since E is open, you can find a ball centered at x of radius, let us say eta, sitting inside E. And if you take a number r, which is the minimum of this eta, comma, delta 1, comma, delta 2, comma, etc., delta n, then for all y in E with norm of y minus less than that r, you can have modulus of dj f at y minus dj f at x is less than epsilon by n for all j from 1 to n. And you take f to be that ball centered at x and the radius this r. Which is that r? It is the minimum of eta, comma, delta 1, comma, delta 2, etc., delta n. So all these inequalities will hold at the same time, and also for all y in S, you can have this. Hope you understood. Now, I am going to start at the point x and move. But when I move, I will move parallel to the coordinate axis only. So how do I move? See, to show that if it's differentiable, I want to show f of x plus h minus f of x, something blah 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 kind of thing. So f of x plus h, I have to compute. X plus h is the increment in x, and f of x plus h is the increment in f of x, right? And while going from x to x plus h, I will move only parallel to the coordinate axis, not arbitrarily. So how do I move? That is what this part explains. So to take an h, very small, norm h is less than r. So write h as h1 etc. hn. So in the linear combination notation, it is sigma j equal to 1 to n hj ej. Okay. Now put V0 as the 0 vector and Vk as this h1 etc. hk, remaining all are equal to zeros. So h1 etc. hk 0 0 etc. 0. So this is my Vk. So in the linear combination notation, it is sigma j equal to 1 to k hj ej. For 1 less than or equal to k less than or equal to n. You do that. Now compute f of x plus h minus f of x. Here remember f is a real function, that's why I am not writing vector f. So f of x plus h minus f of x is equal to, so what is h? It is h1 etc. hn. So in other words, it is Vn. H is Vn. So f of x plus h minus f of x, and what is f of x? It is f of x plus 0. That means f of x plus V0. So this expression is actually f of x plus Vn minus f of x plus V0. Now you do some kind of telescoping. So how do you do that? So this is f of x plus Vn minus f of x plus Vn minus 1 plus f of x plus Vn minus 1 minus f of x plus Vn minus 2 plus etc. plus f of x plus V1 minus f of x plus V0. Right that way. So subtract and add many things in between. So I will get sigma j is equal to 1 to n f of x plus Vj minus f of x plus Vj minus 1. Hope you understood. Okay. Now I have started with an h with norm h less than r. That means square root of modulus of h1 square plus extra plus modulus of hn square, that itself is less than r. But Vk consists of only first k terms, remaining all are equal to zeros. So norm of Vk, what is that? Square root of h1 square plus etc plus square root of hk square, that is less than or equal to square root of modulus of h1 square plus etc plus modulus of hn square, which itself is less than r. So norm of Vk is also less than r. Understand? Norm of Vk, since it is less than r for 1 less than or equal to k less than or equal to n, and since S is convex. Why S is convex? Because S was a ball centered at x. All the balls are convex. The segments with endpoints x plus Vj minus 1 and x plus Vj lie in S. So why is x plus Vj minus 1 lie in S? S is ball centered at x. So how do I show this point lies in that ball? Whenever the distance from that center of this point is less than the radius r. So norm of x plus Vj minus 1 minus the center x. So it is norm of Vj minus 1, which is given to be less than r. So this point lies in S. Similarly, this point also lies in S. So these 2 points, x plus Vj minus 1 and x plus Vj, both lie in S. And S is convex. So not only these points, but also the straight line segment joining these 2 points also lie in S. Hope you understood. Let us move to the next slide. This is a picturization or visualization of what is happening. So this is the ball S sitting inside E of radius r, centered at x. This is the center. And here is, so I am moving parallel to the coordinate axis. So you can think that this is the first axis, this is the second axis, and so on. We are sitting inside Rn. So there are n directions in which we can move. So assume that this is x plus Vj minus 1, and this is x plus Vj. So here I am moving parallel to the coordinate axis. First like this and then like this. Okay. Now these 2 points lie in S because S is convex. Sorry, these 2 points lie in S because their distance from the center x is less than r. Norm of x plus Vj minus x is precisely norm of Vj, which is less than r. Similarly, this distance is also less than r. And since S is convex, not only these 2 points lie in S, but also the line segment joining these 2 points also lie in S. Okay. Now let me parameterize this line segment. joining x plus vj minus 1 and x plus vj. So how do I do that? Parameterization. Line joining the points A and B is 1 minus p into A plus p into B. So use that formula. So gamma j of t is equal to the jth line segment I am parameterizing. So call it gamma j. So gamma j of t is equal to 1 minus p into the first point x plus vj minus 1 plus t into the second last point x plus vj. Here vector x is there. Now you simplify and write this as x plus vj minus 1 plus t hj ej, because so many things will cancel out. For example, this minus tx and plus tx, they cancel, and finally you will get this. Okay. So again I have drawn that figure once again. Here I have drawn E, not the ball S. S is sitting inside E, that is there. So this is the line joining x plus vj minus 1 and x plus vj. Here I have not shown my x, and this is my parameterization gamma j as in the previous slide. Now use mean value theorem. Mean value theorem to what? See, mean value theorem is applicable when we have real functions. So remember, we are considering the case m equal to 1. That means f is a mapping of E into R. So f is a real function. F is from E to R. And gamma j, that is parameterization. So you have the interval 0, 1, and gamma j maps this interval 0, 1 to this line segment. Now take the composition, f composite gamma j. That means the value of f along gamma j. That is a real function defined on closed interval 0, 1. So now you can apply mean value theorem. Mean value theorem says there is some point. For each j you can do this. For each j you can do this. So there exists a gamma j in open interval 0, 1 such that f of x plus vj minus f of x plus vj minus 1 equal to the distance between these 2 points. What is that distance between? F of b minus f of a equal to b minus a into f dash c. Thus c is a point in between 0 and 1. So that is what is precisely mean value theorem says. So what is b minus a? Length of that interval. So here what is the length of this segment? It is precisely norm of x plus vj minus x plus vj minus 1. So x and minus x cancel. You have norm of vj minus vj minus 1. So but what is vj? It is the n tuple h1 etc. hj comma 0 0 etc. 0. And what is vj minus 1? It is the tuple h1 etc. hj minus 1 comma 0 0 etc. 0. So what is vj minus 1? Finally, the first j minus 1 coordinates cancel each other and get 0 0 etc. Jth coordinate is hj, remaining all are equal to 0. So that is the distance. So hj into derivative of f, derivative of this composition. So djf at the point x plus vj minus 1 plus theta j hj ej. I want you to justify this step. My explanation is still not complete. Since this is a kind of recording, I have so many limitations. So you please go through this step. I want you to understand this step. We can apply mean value theorem for this composite function, this composite gamma j, and obtain a theta j in open interval 0, 1 such that you call this composition as Gj. Gj is equal to f composite gamma j. So Gj of 1 minus Gj of 0 equal to 1 minus 0 into Gj dash of theta j. That is what you will get using mean value theorem. But that is precisely saying this expression. What is Gj of 1? What is Gj of 1? This precisely f composite gamma j of 1. This precisely f of, what is gamma j of 1? X plus vj. So it is f of x plus vj. Minus, what is Gj of 0? It is f at x plus vj minus 1. Like that it goes. And you apply mean value theorem to each of the composite functions f composite gamma j and obtain this step. Hope you understood. Okay. Now you start compute this. Modulus of hj dj of f at the point x plus vj minus 1 plus theta j hj ej, that means this quantity, minus hj dj f at x. X is somewhere here. Here is your x. And this point x plus vj minus 1 plus theta j hj j, that lies somewhere here in that line segment. So value of the partial derivative at this point in that line segment, namely this point, minus value of the partial derivative at the point x multiplied by hj. Now take the absolute value, modulus of that. Understood? So mod hj comes common, and you have modulus of djf at this point minus djf at the point x. But in the previous slide, here, whenever the point y lies within a distance less than r from x, then you have this distance is less than epsilon by n. Understand? So use that result. So this point, so this point lies within a distance less than r from the point x. So the distance between them is less than epsilon by n from 1. So it is less than mod hj into epsilon by n. Hope you understood so far. Let us move to the next slide. Now recall f of x plus h minus f of x. We wrote in this form by subtracting and adding so many things and putting it up in a telescopic sum. We have written like this. So now you compute f of x plus h minus f of x minus this quantity sigma j equal to 1 to n hj dj f at x. So replace f of x plus h minus f of x with this expression. So there is a sigma here. That sigma is this, and another sigma which is here. So we have two sigma running from 1 to n. So f of x plus vj minus 1 minus f of x plus vj, I think this is vj and here it is vj minus 1. Sorry for that mistake. Minus sigma hj dj f at x, this thing, equal to modulus of sigma j running from 1 to n. Using mean value theorem, we got a theta j for this expression. So substitute with that. So here I have sigma j equal to 1 to n hj dj f at x plus vj minus 1 plus theta j hj ej minus this expression as it is hj dj f at x take mod hj common, so less than or equal to sigma j is equal to 1 to n mod hj into this quantity was less than epsilon by n. The difference between modulus of dj f at x plus vj minus 1 plus theta j hj and dj f at x, that was less than epsilon by n from the previous slide. Okay. Now sigma j equal to 1 to n mod hj, that is less than or equal to n times norm of h. I want you to prove that. The proof is very simple, and you have epsilon by n as it is because it is independent of j. So this n and this n cancel each other, and remaining is norm h into epsilon. Understood? For all h such that norm h is less than r. Remember, I had assumed norm h is less than r and started all these computations. So what does this say? So I can assume that norm h is not equal to 0 or h not equal to 0 and divide by norm h. Divide what? This expression. So let us move to the next slide. So in other words, whenever norm h is less than r, I have this expression is less than, I have this expression, oh no, I have this expression divided by norm of h is less than epsilon whenever norm h less than r. That means what? Limit of this expression equal to 0 as h tends to 0. So limit of modulus of f of x plus h minus f of x minus sigma j equal to 1 to n hj dj f at x divided by norm of h is equal to 0. Remember what is differentiability? Something like this, right? If such a kind of thing happens, then we say f is differentiable at the point x. And here I should get a linear transformation applied to the vector h. Is this a linear transformation? Sure. So what is this? It is d1 f at x into h1 plus etc. plus dn f at x into hn. So it can be written in this way: d1 f at x etc. matrix dn f at x, this matrix into the vector h1 etc. hn. So this matrix or this equivalently this linear transformation applied to the vector h. This into this is precisely this expression, right? So this expression actually stands for a linear transformation applied to the vector h, namely h1 etc. hn. So this is precisely saying f is differentiable at x, and that f dash x is the linear transformation which assigns the number sigma hj dj f at x to the vector h is equal to h1 etc. hn. Understand? So we got f is differentiable. What did we assume? We assumed all the partial derivatives are existing and are continuous, and we showed that f is now differentiable. Now I have to show f is continuously differentiable. That means the derivative of f, namely f dash, is continuous. So we have observed that the matrix of the linear transformation f dash x is precisely this 1 by n matrix d1f at x etc. dnf at x. Now what is our assumption? The partial derivatives d1f etc. dnf are continuous functions. All these are continuous. So f dash x is also continuous. That means derivative of f is continuous. That means f belongs to C dash E. So this is what we want to prove. Now I am asking you, if all these are continuous, d1f etc. dnf, why the linear transformation is continuous? That is precisely application of this result. This result we have already proved when we proved certain results on operator norms. So suppose that E is a metric space and I have a mapping of E into L of Rn, Rm, and L of Rn, Rm is already a metric space equipped with a metric, and that metric is induced from the operator norm of A minus B. That will give you distance between A and B, whenever A and B are linear transformations from Rn to Rm. Okay, now suppose that I have such a setup. Here P is a point in E. Correspondingly, for each P in E, I will get a linear transformation from Rn to Rm denoted by AP. So I have a mapping from E to L of Rn comma Rm written as P going to AP and whenever I have Q close to P, AQ is also close to AP. This we have proved. That is, this mapping is continuous. And that happens if and only if. That happens if and only if. See, AP is a linear transformation from Rn to Rm. So it has got a matrix with respect to standard basis for Rn and Rm. If there is a matrix, naturally there are entries in that matrix. And if that entries are continuous, this mapping P going to AP is also continuous. Whenever the entries of that matrix are continuous, the mapping P going to AP is also continuous. So that is what this says. The entries of the matrix for f dash x, they are continuous functions of x. Therefore, the mapping x going to f dash x. Instead of P, I am using x. The mapping x going to f dash x is continuous. This is precisely saying this is in C dash E. Understand? So this is not a very small theorem. It is a bit lengthy proof, but ideas are very simple. You can enjoy and write the proof. Thank you.